Okay, in this example, we're going to use Thevenin's theorem to calculate the voltage across this circuit, this part of the circuit up here. And I've tried to break this down into some steps that will follow on a couple of different examples. Um, these steps work specifically for circuits that have no dependent sources. Okay, that's an important caveat. First thing that we'll do is we'll treat the load as an open circuit. So what I mean is the load on the Thevenin equivalent. Remember that we're shooting for this Thevenin equivalent, which is going to be a Thevenin resistance, a Thevenin voltage, and then whatever blob we put in here is the load on the Thevenin circuit. In this case, it's this resistor. Okay, and we're being asked to find the voltage. So we treat it as an open circuit, which means we pull the resistor out and we treat this as if it were open. Okay, so then we'll calculate the Thevenin resistance. To do that, we just pull all of the sources out of the circuit, treating them the way that they're supposed to be treated, and then calculate the effective resistance from A to B, which I just randomly assign values to the nodes to highlight this point. Then we'll use superposition to calculate the Thevenin voltage, which is the voltage across the open circuit, V naught. And then we'll finally draw the Thevenin equivalent and solve for the unknown. Okay? Alright, let's give it a shot. So the first thing that we'll do is we'll calculate the effective Thevenin resistance, RTH. And remember, to calculate the Thevenin resistance, we treat the circuit as if all the sources have been removed and then add up the resistances. So we'll just obey our rules here for sources. The voltage source is shorted and the current is left open. So it literally ends up looking just like this. Okay? And we need to find the effective resistance between here and here. So if you stare at this for a while, you'll convince yourself that the 3K and the 6K resistor are in parallel to one another, and that those two are in series with this 2 as we travel from A to B. So we can really quickly then reduce this and solve for the Thevenin equivalent. Thevenin resistance, well, a 3K and a 6K in parallel ends up being a 2K resistor, and then a 2K plus a 2K is 4. So R Thevenin equals 4K ohms. Okay, so our first part is done. The next thing that we'll do is we'll look at the individual sources alone. So we'll remove all other sources from the circuit and then look at the voltage that is provided across this open circuit by a single source. Let's start with 1, which is the voltage source. So I'll draw the voltage source in, and I'll draw the circuit with the other source removed. Okay, and now you could draw this like this. Okay, but this is open, so all of this can get removed. And this is sort of how I think my way through the solution here. That's all removed. Remember, we're looking for this, plus, minus. Okay, and what's the voltage across this resistor here? It's got to be 0. There's no current. Okay, it's an open branch, so it's completely dead. So that means this node of VOC is dead here. We could even move it down here and it's still dead, right across the resistor, across here, all the way back to this node here. And it's the same, whatever value VOC has, it doesn't matter where we put that negative terminal. So when you look at it that way, you can then see that, look, we could bring it right down here, and we could say that this is VOC. Oh, well then, VOC is simply the voltage across the 6K resistor. And we can solve that using voltage division. So VOC then equals 12 times 6K over 9K. And if you do that out, you'll find that the voltage is 8 volts. Okay, and let's say that's give that a single prime. Okay, that was easy. Now let's look at the current source, and we'll remove the voltage source. So that's going to be a short. I think the hardest thing about these circuits is figuring out it's getting accustomed to dealing with the open circuits and the shorted circuits and being able to read exactly what it is that's going on here. For instance, here, what's going on with this circuit? Well, the current in here cannot flow into this branch. There's no way for it to happen. You can convince yourself if you try and do KVL at this node if you're not convinced, and you'll find that you can't get anything to make sense as far as getting the currents to sum up to 0. So not possible. That means that this is a dead part of the there's no current through here, there's no current through here across the resistor. And you can see again what I'm doing is I'm just bringing myself to realize that I could do this. I could have this measure this voltage here by putting the positive terminal down here, the negative terminal up there, and that would also give me the voltage here, which is voltage double prime. And so now that's an easy one to solve. The nice thing about this, you want to pay attention to the polarities, okay? Because of the current flowing in this current source, to label the resistor with the correct sign convention, we would need to have positive, negative, like this. And that tells us that the voltage across the resistor is the same in magnitude and in polarity as V double prime OC. And so that's simply just 2m times 2k, or 4 volts. Okay, so bringing this all back together now, the thevenin is what we're solving for. Thevenin equals V prime plus V double prime on the open circuit, and that equals 12 volts. Okay, so we have our thevenin and we have Vthevenin, and we're ready to solve our circuit. Let's draw the circuit out and see what it looks like. And remember that the thing we were looking for was a resistor, a 4K resistor. Okay, so we have our 4K resistor right here that we're solving for. This is our thevenin resistance, which is 4K as well. So that's just a coincidence. And then 12. And we were asked to find the voltage across the resistor. Okay, so we'll draw it in the way it was drawn in above, because we want to make sure that it's actually a positive value. So current's going to flow this way. So our voltage will be positive. And now we can just use voltage division. Okay, so V naught then equals 12 times 4 over 8K, which is really just 6 volts. Okay, so that's our answer. As a quick aside, we can also solve this circuit using the idea of source transformations. And in fact, it'll yield a much simpler and faster result. Let me show you how that would work. And this is entirely seen by inspection and just getting comfortable with looking at circuits and seeing source transformations. So if I took that 12 volt, let's take a look at it here. If I take this 12 volt source here, which is in series with this resistor, and I convert it into a current source in parallel, then I would have a 3K and a 6K in parallel. I can convert those into a 2K resistor, which is a number that you'll start to memorize after you've done a bunch of the homework problems, because it comes up over and over again. And so let's just do that really quickly. So using source transformation, I can replace it with a 12 divided by 3, a 4 milliamp current source. And I'm just going to go ahead and combine those two resistors. So that's 2. And now I have a circuit that looks something like this. Well, now I could go ahead and convert both of these into voltage sources. And you'll see what falls out of this. Voltage source here will be 8 volts. And if this is confusing, then watch the video that I put out on source transformations. Okay. And here the voltage source will be 4 volts, and this will be 2K. Okay, and then this is our unknown that we're looking for. And this is solvable by inspection. We get thevenin equals 12, and our thevenin equals 4K ohms. Okay, so using source transformations can sometimes greatly simplify the process when you're dealing with a Thevenin circuit.